So now we introduce stationary distributions associated with a Markov chain. So we will explain this via an example. So consider a transition matrix for social mobility. So this is a transition matrix. That means every row adds up to 1. So 0.8 plus 0.1 plus 0.1 is 1. 0.2 plus 0.6 plus 0.2 is 1. And similarly, you add the third row, it is 1. Notice that the columns may not add up to 1, but the rows have to add up to 1. So let us first give the names of the dimension. So say the first column is lower class, second column is middle class, and U is upper class. Similarly, you have lower class, middle class, and upper class. So this 0.8 means you started in the lower class. With the probability of 0.8, you will remain in the lower class. With the probability of 0.1, you might end up in middle class, and probability of 0.1, you might end up in upper class. So say if you started in middle class, you could end up in a lower class with probability 0.2, or you could remain in the middle class with probability 0.6, or climb up the social ladder and go to upper class with probability 0.2. If you started in upper class, you could have a bad luck and move down to a lower class with probability 0.3, or you could move down to middle class with probability 0.3, or you could remain in upper class with probability 0.4. So there is social mobility. People can move from lower to middle class to upper class, and upper class to middle class, and so on. So there is all possible mobility. So although people move from lower state to middle state or higher wealth state and vice versa, the proportion of population in these states might remain constant. So although there is social mobility, but the proportion in each of the states might remain constant. So for example, if you have something like this, a transition matrix, all the people are moving, but overall you will always have 55% of the people in lower class. So that is right here. So for this transition matrix, we will have this stationary distribution. That is 55% of the people will always be in lower class, 27% people will be in the middle class, and 18% people will be in the upper class. All the people are moving, but the percentages of the population in lower, middle, and upper class remain constant. So this is a very useful way for modeling social phenomenon, that although there is intermixing, or even for genetic populations, the proportions remain stationary. So this you can express in this format, pi times p is equal to pi. So pi is the proportion. So this is matrix P. So you multiply this with pi 1, pi 2, pi 3. So this is your initial proportion. So these initial percentages, then you multiply this, then there is some mixing, but even after mixing, this is again equal to the initial percentage. So 55% gets split down to lower, middle, and upper. 27% also gets split down. 18% also gets split down. But when you add them back up again, they again come back to the same percentages. So this is what this formula is. So our objective is to compute this pi, that this stationary distribution, from our transition matrix P. So this data of social mobility you could compute from big data available to you. So these days we talk about a lot of big data analytics. So if you have a big data about, say, computer programmers, so you can see how much are working on a lower salary, a middle salary, and an upper salary, and then you can see how many people actually moved up the ladder or down the ladder, and get a transition matrix. So we can rewrite this matrix as like this. So we have just multiplied pi 1, pi 2, pi 3 with this. So you get 0.8. So you multiply this with this, you get the first equation. You multiply this with the second one, you get the second equation. You multiply this with the third one, you get the third equation. The only problem is when you add this up, so this will become pi 1. So 0.8 plus 0.1 plus 0.1, because the row sums up to 1. And this will add up to pi 2, and this will add up to pi 3. And this one also adds up to pi 1 plus pi 2 plus pi 3. And These three are proportions, so this is equal to 100%, or in terms of probability 1. So these proportions, if you add up, this is 100%, but if you write in terms of probability, this is just 1. So these equations are dependent on each other. So we will skip this third equation completely, and so we will skip this, and instead of this equation we are going to write this equation, and that's what we do. We write this equation. So notice the first equation, you subtract pi 1 from here, so 0.8 minus 1 will give you minus 0.2. Rest you just copy as such. In the second equation you subtract pi 2, so 1 minus 0.6 will give you minus 0.4, so you get minus 0.4. Rest you copy as such, and this is this equation. In a matrix format you write it like this: pi 1, pi 2, pi 3 times, say, this matrix A is equal to 0, 0, 1. So this is I'm just rewriting these equations in the matrix format. So now to compute your proportions, you just compute A inverse. So pi is equal to A inverse times 0, 0, 1. So this I'm writing as pi. So you take A on this side. So see, there is 1 here. So 0, 0, 1. This 0, 0, 1. So you just have to read the third row, and the third row will give you the result, and the result will come out to be 0.55, 0.27, and 0.18. So in R, you first write down the matrix. So you write down this matrix P. So 0.8, 0.1, 0.1, that's what we're writing: 0.8, 0.1, 0.1, then 0.2, 0.6, 0.2, so 0.2, 0.6, 0.2, and then finally 0.3, 0.3, 0.4. So 0.3, 0.3, 0.4. Write down as such. Your by row is true, number of rows is 3. Then you always subtract 1 from the diagonal element. So you just focus on the diagonal element. So the diagonal elements are these two and then this element. So this element you forget for now. You take these two elements and subtract 1 from it. So 1 minus 0.8 will give you minus 0.2. 1 minus 0.6 will give you minus 0.4. Rest of the elements you just copy them as such. So notice that these two have not changed. You copied them as such. This and this is the same. You copy them as such. And the last column you always add 1. You replace this with 1, 1, 1. So that is why, because we have replaced the third equation with 1, 1, 1. So this is the third equation. You always replace this with 1, 1, 1. And that's what we do. You subtract 1 from the diagonal element, 1, 1, 2, 2. You again subtract from the diagonal element. And for the third column, you take 1. So if this is a 4 by 4 matrix, again you don't have to worry much about it. Fourth column you set up as 1, and from the rest of the diagonal elements you subtract 1, and that is it. You invert it and take the third row. The third row gives us the answer. So solve P is what will invert this matrix. So I first adjust this matrix to this. So I feed in this matrix, then convert this matrix to this matrix, call this matrix also as P, and then solve P will invert it. So this will invert the matrix. So I will invert it and see the third row. Third row gives me the answer. So let us see this in R. So let us run this. So this is the third row. So you get 0.545, 0.272, and 0.1818. So this is our answer for the solution. So this 3 means we are just focusing on the third row. And this is the P, this is the matrix I'm finding the inverse of. So you see this is precisely the matrix which is written in the slide right here. So this is the matrix which we have right here.